A research team in the School of Engineering is investigating the dynamics of pollution in flowing water. It's hoped it'll lead to a greater understanding of how environmental damage is caused in riverbeds and along our coastlines.
I'm Jonathan Pearson. I'm an assistant professor at the University of Warwick. I'm interested in mixing due to the effects of waves. So essentially we're in the coastal region here. And essentially we're looking at how a pollutant spreads due to the effect of wave activity. So in the offshore region we may have a pollution spillage or a sea outfall which puts pollution into the sea, and we're interested in how the waves influence the pollution. And in a sense, does it increase the mixing or does it decrease the mixing?
Now, because of the nature of the subject, I presume it's not very easy to carry out an experiment on location.
No, indeed, and it's also very expensive. Essentially what we do is we build smaller models actually in the laboratory, and here we have a facility here which allows us to conduct detailed measurements at small scale, and then we can scale those up at large scale and then see if there's any influence between small and large scale measurements.
So what have you found out so far?
Well, it's quite interesting really, that in the offshore region we found that wave activity doesn't have a significant effect on the mixing. So essentially the spreading of the pollution or the dye plume which we input into the facility doesn't increase significantly. However, when we go into the nearshore region, where the water depth is much smaller, then the mixing increases significantly. If you have a pollution source which is drifting inshore, you may have high concentrations of chemicals, but if you have wave activity in the nearshore region, then those chemicals can be spread out and then the peak concentration will reduce. One of the reasons is that most of the pollution which is discharged into the sea tends to occur after storm events. We've got big rainfall events and the sewer systems can't cope, and what happens is that the pollution goes into the nearshore region. But of course when we've got storm events, naturally we have larger waves. So if we've got larger wave activity, then the rate of recovery in the coastal region can be significantly reduced.
So what is it you're trying to achieve here?
Well, two things really. One is how quickly the pollutants are broken down. So that's the first thing sort of in the water column. So do the waves force the pollution further inshore, or do the waves force the pollution offshore? But also we're interested in how the pollution goes into the bed. So do the waves force the pollutants further into the bed, or do the waves actually wash the pollutants out?
A landlocked Midlands university isn't the most obvious place to carry out research of this kind.
Absolutely, but there again, if we've got the facilities here, then it doesn't really matter where you do the research. Basically we've got a small scale facility here which allows us to simulate the experiments or simulate the measurements which we can also conduct offshore. And it's not too far to the coastline, it's a few hours really.
My name is Klaus Richter. I'm assistant professor here at the University of Warwick in the Department of Civil and Structural Engineering. I'm focusing on environmental processes, especially in rivers. So I'm looking at the transport of contaminants like solutes or sediments in the riverine environment.
And how exactly do you do that?
We are doing this by introducing a tracer, so a conservative pollutant. And we are actually measuring this tracer while it is flowing down our model river.
So what are you actually doing here in the laboratory?
Here in the laboratory we are especially focusing on quantifying the exchange processes of pollutants, of contaminants between the main river flow and the riverbed. What we found so far in real experiments, in the real environment, is that there is actually exchange process between the main river flow and the riverbeds. And we are trying now to use laboratory setups actually to quantify the exchange processes using different sediment types, so for example gravel beds or more sandy riverbeds, and different flow depths, so the different elevation of the main water body and different height of the riverbeds, to quantify the exchange processes of pollutants with the riverbed.
What are the practical benefits of this research?
At the end product we would like to have some design guidelines for environmental authorities like the Environment Agency, because under the new constraints of the European Water Framework Directive we have to prove what pollutants will actually harm our environment. And therefore this is quite novel or recent research, which was never done in this detail before.
What are you trying to achieve here ultimately?
What we would like to achieve is to use our data to be able to predict the rate of exchange of pollutants from the main river flow into the river beds, because actually these pollutants might build up in the riverbed and therefore might harm the ecology in the riverbed.
My name is Ian Geimer. I'm Professor of Civil Engineering in the School of Engineering at the University of Warwick. We're off the side of the M5 motorway, and this is one of the sites that we've been using to look at the impact of highway drainage on receiving water ecology. What we're trying to do is to work out where material that's washed off the carriageway when it rains actually ends up in the receiving water, in the rivers. The main problem is material that's attached to sediment, so contaminants that are attached to sediments. Where these sediments actually deposit in the channel, they can have an adverse effect on receiving water ecology. The main types of pollution being washed off motorways are either metals, dissolved metals, either zinc, cadmium, copper, or PAHs, petrol derivatives, chemicals from the burnt petroleum that the cars use, and they're washed off, mainly attached to sediments.
So what are you doing today?
What we're doing here today is just simulating a rainfall event. Clearly it's not very easy to actually come out and monitor everything when it's raining, and so what this is a controlled experiment to look at what happens to material if we had an overflow event, and we're using the dye as a tracer to tell us where the water actually moves. We can take measurements to show what concentrations occur in the water. What we're actually doing is we're introducing the tracer into the drainage system from the highways. It's then being discharged into the river system as it would do under a storm event. By taking the measurements, it tells us how far across the channel the material will mix, and therefore what sort of concentrations we can expect. If we know these sorts of concentrations, we can then go to the biologists, ask the ecologists what impact this has on the receiving water.
Now, you personally have been researching this subject for about 25 years now. What do you hope to achieve by the end of it?
What we're hoping to do is to provide some practical guidance to the Highways Agency so that when they're designing or assessing the impact from outfalls, they can do it knowing the impact it's going to have on the receiving water and taking that into account.
Where are you at with this research and what happens now?
Well, we've just come to the end of a 5-year programme of work. The work is being written up as a new guidance manual for the Highways Agency, and that will be launched towards the end of this year. What we would like to do is to follow this up with some more detailed studies looking at where specific sediments deposit in relationship to the channel characteristics. So say the vegetation in the channel, does it deposit around the vegetation? Do we have a specific area where we have problems?